Right, year 12s. I spoke for quite a lot, I think, on another video, so I'm going to try and shorten this one, and we'll break this next section down into a couple of lessons worth. We don't have to do everything in a rush, okay? So section 2 of chapter 5, and we're still looking at when a force is a function of x. And we're going to say the concept at the beginning of this chapter is that work done by or against the force, you integrate that function with respect to x between two values of displacement, and you either get the work done by a force or the work done against the force. And we remember that work done and energy have the same units, joules. They are largely interchangeable, okay? And that's very important for this next section. Right, rather than read this to you, I want to highlight the important bits, okay? So, in this section, we're talking about elastic strings or springs, okay? We're talking about things that can stretch, and when you've stretched them, there is a tension in them. As you stretch them, there is something wanting to pull your hands back together. And the further you stretch them, the bigger the tension. Now, strings can be stretched, but if you push the ends in together, you just get a lot of slack string. A spring, on the other hand, you can stretch, you can compress it, you get a force in both directions. Stretch a string, you get a tension. Squash a spring, you get a thrust. So there is an important difference between that letter and that letter. Strings have a tension if you stretch them. Springs have a tension if you stretch them, and a thrust in them if you compress them. And for both of them, the force is proportional to the compression or extension, okay? So if it's tension, and we say that this is a positive proportionality constant, tension will be in the opposite direction to an extension. If you extend it, the tension is that way. If you squash a spring, the force is that way. So I'm going to say the tension and the thrust are a positive value multiplying x, but then the whole thing is negative if x is a displacement, making both x and t vector quantities. Right, there will be two ways we can describe it, as in key point 5.2. You've got a book, you can read this in more detail. We will either say t equals minus kx, k is the stiffness, is one way of defining it, or in some questions we will replace the k by two different letters, lambda, the modulus of elasticity, and L, natural length. So we can replace K and lambda upon L are the same thing. Right, and that is called, if I didn't already write that somewhere, that is Hooke's law. That the force in a string on a spring depends on displacement, which means it's one of these examples. So we have a whole host of 1, 2, 3, 4, a proof, another example, 5.10, 5.11. I'm thinking, since I tend to lump everything together, and I'm getting an impression sometimes we do too much in one go, let's aim this time with our time for you to work your way through and understand that example, that example, that example, and that one, getting to the idea of work done extending elastic spring. So these examples all use the equations, the formula, these two formula here, finding the force from an extension. So for example, a light elastic spring has a modulus of elasticity 85. That's a value of lambda. So that would be this expression. And a natural length is given. Notice in meters. Newtons, meters, what's the other thing I'm looking for? Newtons, meters, seconds. We're going to be still working in SI units, but seconds isn't relevant to this. So that's finding a force from lambda x upon L. A light elastic string is attached to a fixed point, hangs vertically in equilibrium. In equilibrium, forces will balance. It's hanging vertically with an object of mass 400 grams. So that's the next one. Newtons, meters, kilograms. 0.4 kilograms. Natural length. Find the stiffness of the string as a multiple of g. The acceleration of gravity. Find the modulus of elasticity. Right. Stiffness and modulus of elasticity from natural length and things. K equals lambda upon L. T equals that. So equilibrium, the only two forces, the tension and the weight, must balance. The tension and the weight balance is what's written here. Okay, so we know what the tension is. Once we know the tension, we can say that's equal to kx and then work that through. So two examples just about these rules and equilibrium. An object of mass not 1.5 kilograms is attached to the end of a light elastic string. The other end is fixed to point A. The object is then held at A and released. The modulus of elasticity is 50 newtons. Find the extension when the object reaches its maximum speed and hence its distance below A at this time. What on earth's that about? So let's have a look at worked example 5.6. Where if I can get everything there on the same page. Right, 8 minutes here. I want to stop by the time we get to 15 minutes. So an object, there's a string attached at A and something is dropped from here and it falls on the elastic spring and we want to find the point where it reaches maximum speed. Okay, the string is 1.5 meters long and it's a string, not a spring. So for 1.5 meters, it just falls under gravity. But as soon as it gets to 1.5 meters, as soon as it passes its natural length, the string will start stretching, so there'll be a tension as well as the object's weight. When the string starts stretching, the tension will be smaller than that, so it'll keep accelerating downwards. So A is positive when 1.5 g is bigger than t. A is negative when t is bigger than 1.5 g. So the maximum speed will be when these two things balance. Before that is bigger than that and slowing it down, so it's going to fall. So it falls at 9.8 meters a second. As soon as the string starts stretching, this tension is increasing, so it's still accelerating until eventually it'll start slowing down. Still keeps going downwards until eventually stops. So the maximum speed isn't the bottom, it's the point where these two things are in balance, okay? When is t equal to 1.5 g? It's when lambda x upon L equals 1.5 g. So 50 times 1.5, the natural length is 1.5. It's the extension we're finding. We want to find the point at which the acceleration is zero, where it goes from accelerating to decelerating, where it goes from going faster, speeding up, to slowing down. So what have we got here? The book says if you multiply by 1.5 and divide by 50, we get 0.44. So that is, where's me red pen? I'll use a different colour. Oh, there it is. They're all hiding under the book. It falls 1.94 meters where it reaches maximum speed. That's not the point it stops at. It keeps falling until eventually the speed becomes zero, which is a slightly different question. Let's do worked example 5.7. Right. Abysmally done in the book. What on earth's missing? A diagram's missing. An object is attached to the lower ends of two parallel light strings. Right. That's an easy diagram, isn't it? Right. So an object is attached to two strings. The free ends are both attached to A, and it hangs in equilibrium. And it's an object of mass 10 kilograms, so I can add a weight to the diagram, 10g. That g is not the same g as in kilogram. That's 10 times 9.8 meters a second, or whatever they want us to use in this question. Right, so we've got two different strings, a tension in one and a tension in the other. Is this a question about stiffness, or is it a question about modulus elasticity and natural length? Modulus elasticity and natural length. So tension 1 is going to be 25 times the extension in that string over 0.5, and tension 2 is going to be 30 modulus elasticity multiplied by the extension in that string divided by 0.4. It's in equilibrium. T1 and T2 balance 10g. Right. Find the distance A to P. Right. Find that distance, D. Right, so D is going to be that length plus x1, and it's also going to be that length plus that extension. Right. The two strings have different lengths and with different stretchinesses. What we do know is if this hangs in equilibrium, they're stretched for the same length. So they've both got different extensions, okay? How does that help? All right, here, instead of that, I could replace x1 and x2 by d take 0.5 and x2 is d take 0.4. So what we get is 25 lots of d take a half over a half plus 30 lots of d take 2/5 over 2/5 is 10g. How do we solve that? We can divide 25 by half, divide 30 by 2/5. So that's going to be 50 d take a half plus divide by 2/5, so divide by 2 multiplied by 5, 1575. And then work that through, okay? We should give the 1.2. But the crucial bit was, and let's, all right, 16 minutes. I said I was going to finish in 15, so just got 2 more minutes. All right. In equilibrium, draw a diagram. If it's in equilibrium, balance the forces. It's a question about tensions. Decide whether you're using lambda x upon L or you're using kx. But this question talked about lambda and L. Right. My suggestion for this week is you go through those examples, make the notes you want. Oh, and have a look at the video I've sent you for the vector questions from practice paper 1, set 1, and that'll do us for this week. And then hopefully we'll find out when we're meeting up in the near future.